Back to the course. So, in single degree of freedom, undamped system, we observe that the amplitude remains constant. That means the energy is not getting dissipated. Okay, because there was no damper in the system. Now, let's analyze a single degree of freedom free damped vibration system. So, here you can see there is a damper with a damping coefficient C. There is a spring as well. Again, I'm fixing the coordinate system at the equilibrium position, which is most important. Okay, and again we have an initial disturbance in terms of initial displacement as well as initial velocity. There is no external force acting on the system. That's why it is called free vibration. Now we will start with Newton's second law. Mx double dot, it will be equal to minus Cx dot minus Kx, because you know the system is acted upon by all these external forces. External forces cancel each other in the y direction, but there is a net force, external force acting in the negative x direction. That's why there is a minus sign here as well as here. So now we will end up with mx double dot plus cx dot plus kx equal to 0. So this is the governing differential equation of the system. Again, I will assume a solution for x in terms of c e raised st. Plugging this back, I will arrive at ms square plus cs plus k into x equal to 0. Okay? Again, from the study of linear differential equations, we know that the solutions of this S1, S2 will be, the possible values of S will be, there will be two values since this is a quadratic equation. It will be given by minus c plus or minus root of c square minus 4km divided by 2m. I hope you all remember these equations. Okay, so one thing to be noted here in comparison to the undamped systems is, here depending upon this value c square minus 4km, if it is a positive value, if it is 0, if it is negative, the solution will be different. Because I hope you remember that a quadratic equation has three kind of roots: real roots, real and distinct. Real and distinct root is the first case, then equal roots, then the other is imaginary and conjugate. So there is a physical relevance as well. So we call those systems this is mathematics. Now coming to the physics of things. So if this C is less than 2 root km, we call it as an underdamped system. If the C value, damping coefficient, is equal to 2 root km, then we will call it critically damped. If C is greater than 2 root km, we will call it overdamped. Guys, I am introducing a new factor called damping ratio given by zeta. So this is C divided by Cc, where Cc is the critical damping coefficient. Okay, so this is damping ratio, which will be unitless. This is the critical damping coefficient. For underdamped, zeta will be less than 1. For critically damped, zeta equal to 1. For overdamped, zeta will be greater than 1. So from the maths, depending upon the value of the damping in the system, there will be 3 different responses to this system. Okay, I hope this is clear. I will continue on the next lecture.